Right, so we will move on to question number 10. Right, so domestic bleaching agents. So bleaching solution contains equal mole amounts of sodium hypochlorite, so NaOCl and Cl minus. And the amount of Cl2 gas liberated by the action of excess diluted acids on a sample bleaching solution is called the available chlorine of that sample. This is shown by the reaction below. So they have given a reaction as well. So it will be advantageous for you guys, because otherwise you need to know what is happening with ClO minus Cl minus in H plus medium, as they have mentioned here. So basically it will produce Cl2 gas and water. So get this information from here. Okay, and generally the available chlorine of bleaching solution is expressed as the amount of Cl2 gas liberated from 100 grams of the bleaching solution. So generally this is just a description, and the following procedure was used to determine the available chlorine in a bleaching solution. So basically they have given an information, so we will get the information from it. So we can use the board here. Right, so we have a 25 cubic centimeter of bleaching solution. Okay, so basically it can contain NaOCl and Cl minus, and it was diluted up to 250 cubic centimeters. So there is no point. So you have this one, and you diluted up to 250 cubic centimeter, and then you take 25 cubic centimeter from this, and excess okay, so then you put acetic acid, basically H plus and Ki. Yeah, so this will liberate I2, and this was titrated with sodium thiosulfate, and this will produce NaI and Na2S4O6. Okay, and sodium thiosulfate amount, so you can balance this one as well. You can put 2 here and 2 here. So the stoichiometry is 2:1. Sodium thiosulfate to iodine is 2:1, and the sodium thiosulfate amount that is consumed is 0.3 m, and it is 90 cubic centimeter. Okay, so basically you know the number of moles of sodium thiosulfate, and you can calculate the amount of I2 that is liberated. Okay, so that is one of the things that you can calculate. But the question asked is write the balanced chemical equation for the reaction of ClO minus with I minus, and the reaction of I2 with sodium thiosulfate. So I2 with sodium thiosulfate is this, and the other reaction is ClO minus with I minus. So basically ClO minus with I minus. They are asking about the overall reaction. So when you see here, there is this reaction that can be happen, right? ClO minus in the acidic medium with Cl minus, there can be Cl2 gas that is formed. Okay, so other than this, there you should add here the I minus. Basically you need to add I minus here. You can see the board, right? Yeah, so one of the reaction that they have given is ClO minus with 2H plus and Cl minus, Cl2, and H2O is formed. Okay, so this reaction is given in the description. That is why I told you to use this one, because this is already given, right? So other than this, when you have this acetic acid in the medium, okay, so this reaction is going to happen because it is driven by H plus. But don't forget, they also have I minus. So what could be happen here with Cl2? So when you have I minus with Cl2, don't forget it can form I2 and 2Cl minus. Okay, so this is the normal thing that can form. Then you can add these two to get an overall reaction if you need, because the Cl2 and Cl2 will be cancelled out, and there will be 2Cl minus, so there is only 1Cl minus. This one also will be cancelled out for a 1, and there will be overall reaction with ClO minus and I minus. producing Cl minus and I2. So that is the overall reaction that you need. Okay, so that is what they have asked here. I will share the screen here for a while. So this is the reaction that they have asked. Okay, ClO minus and I minus, ClO minus and I minus reaction, the overall reaction, and iodine with sodium thiosulfate is this reaction. This is very common that we have discussed up to million times now. And calculate the percentage of available chlorine by mass in the bleaching solution. So you can understand they have given this density. So this is the second place that we are going to use density again. So earlier we used the density for chromium in the case of question number 8 to calculate the thickness. So this is another place that they have given to use this density T, right? So calculate the percentage of available chlorine by mass in the bleaching solution. So you can imagine what is actually happening here. When you consider about the overall reaction, you know the amount of iodine present. So I will stop sharing the screen now. So you can see the board now. So you need to know iodine. If you know iodine, which means you know Cl minus, what is the amount of Cl minus, or either if you know iodine in this particular reaction, you know amount of chlorine that is produced. But it is not necessary, because if you know iodine, you know Cl minus, then in this one, you know it is present as an equimolar mixture. So you know what is the number of moles of OCl minus as well, because they have mentioned that it is present as equimolar mixture. So if you know Cl minus, which means you know the moles of ClO minus as well. So how to calculate I2? So that is why they have given this information. Okay. So they have given 0.3 m sodium thiosulfate. They have consumed 19 cubic centimeter. So you can calculate number of moles of sodium thiosulfate. And the stoichiometry is 2:1. So you can calculate the liberated I2 amount. So you just need to divide it by 2 because 2:1. And then if you know I2, then you can calculate the amount of Cl2 that is present. Okay. So primarily what you have to do here is you know the thiosulfate moles. Then you calculate I2 moles, just you divide it by half. And this would be equal to the amount of ClO minus moles, which will be here 0.3 into 19 into 10 to the power minus 3 of sodium thiosulfate, and half of it is I2 number of moles, and this will be equal to ClO minus at the end of the reaction. And but don't forget, this is in 25 cubic centimeters, so you need to multiply it by then 10 to get the number of moles in 250 cubic centimeter, because initially you have a 25 cubic centimeter, but we added water to dilute up to 250. Then from that solution we took 25. So you can imagine the number of moles here is reduced by 10 times. So if you know the number of moles of ClO minus here, you need to multiply it by 10 to get the total number of moles, right? So if you know ClO minus number of moles, you know now that should be the same amount that is present as Cl minus, which is Cl2. So you know the number of moles of Cl2, then just you need to multiply by the molecular weight of Cl2, which is 71 grams. And then what you have to do here is, if you then you know the mass of Cl2, then you need to show that as a percentage. So to show the percentage, then you need the mass of the solution, bleaching solution. So you know the weight of Cl2. You need to know the weight of the solution, then you need to multiply it by 100 to get the percentage. You know this from this calculation. But how do you calculate this? For this, they have given the information, that is 25 cubic centimeter, which is you used initially, which is the volume of the solution. And then you need to multiply it by the density. That is where the density comes. Okay. So this is the place where you use density here. So you multiply 25 cubic centimeter by the density, but don't ask why I take 25, not 250 cubic centimeter. Because think about the number of moles. The number of moles present in 25 cubic centimeter will be same as present in 250. Okay, because it's like you have 10 mangoes here in 25 cubic centimeter, and then you add water. So to make it 250 cubic centimeter. But the number of mangoes doesn't change. This is same way. You have Cl minus same number of moles. Just you add water to dilute it. The concentration changes when the dilution happens, but the number of mole will not change. Okay. So based on this, the original solution is this one. So that is why we have 25 cubic centimeter of the original solution, and then you multiply it by the density to get the mass of it. So it will be 30 here. This will be 30, and you know now Cl2 that is present based on this calculation. Then you can find the percentage. Okay, so that is how you calculate this question, right? So moving on, I will share the screen now. So that is how you calculate for this particular question, part 2. Okay. And second one is following questions based on the transition. So iron, again iron. So iron is continuously coming here. So ground state electronic configuration of iron, straightforward and simple. And most common oxidation states +2 and +3. And aqueous FeSO4 reacts with KCN to give a yellow. Okay, so we have to use the board a little bit here also. So I will stop sharing and share the question for myself. First two questions are very straightforward and simple. So the second thing is so we have FeSO4 and you need to react with KCN and it gave a yellow color. So if you can remember about the reaction with Fe with Fe, so basically FeCN 6 4 minus and octahedral ionic. So this is an ionic complex, right? So ionic complex. So if you remember about Fe2 plus reacting with Cn minus, if you remember about your D block chemistry, this is the complex form is FeCN6 4 minus. That is the ion, the negative, the anion, but the complex is instead of having 4 minus, you can have this potassium. So this will be K4 FeCN6. Okay. The oxidation of state of Fe remains unchanged during this reaction. So basically, you can understand here this is +2, and in fact here this is also +2. That is why this is -6. So +2 minus 6 is -4. So to balance this -4, there should be 4 times of K plus. So that is how this complex is formed. Okay. The molecular formula of L is Fe. What is this L? Formula of L is Fe K2C5N6O. Write the structural formula FL. Oh, now this is totally different because they have given the molecular formula is Fe and K2. What is the other one? C5. Wait, I will check with the evaluation. So that is easy for me. Okay. Where I am reading this. Okay, so I am in a question number 5. So this should be question number 3. Okay. So yellow octahedral, the G does not contain elements hydrogen, oxygen, and sulfur. Write the structural formula of G. So basically, this will not contain hydrogen, oxygen, and sulfur. So you can imagine when this is reacted with this one is formed. So they are asking about the structural formula of G. So this is the structural formula of G. K4 FeCN 6. And then they are asking about give the IUPAC name of G. So you can explain. So I have explained to you many times how to write the inorganic IUPAC name. So first you write down the positive ion. Here, since we have 4 potassium ions, so we don't use quadra potassium. No, we just write down the name of the element because these will have a stable common configuration, like this stable common oxidation state. So this is potassium. So you need to separately write potassium. And you need to keep a small space here. And then you start naming the complex. But don't forget this complex is negatively charged. So you cannot use ion. You need to use suffix ate. So this is Latin name with suffix, which is ferrate. So basically hexacyano, which is 2014 cyano is okay. But now you cannot use cyano. So this should be hexacyanido. You need to use ido suffix now. Okay, according to the new syllabus. So hexacyanido ferrate, and what is the charge? That is 4 minus, which in this case the oxidation of iron is +2 because they have mentioned the oxidation state. Okay, that is FeSO4 reacting with this cyanide. Okay, still it should be Fe2 plus. So basically potassium hexacyanidoferrate 2 within brackets in the Roman numbers. Right, so the next question. So I would like to share the screen as well now. Okay, so this was potassium hexacyanidoferrate 2 and give the IUPAC nomenclature we have mentioned now. And then they have telling some other things. Okay, so we have G now. Okay, now this is G. We have G here. Okay, so this is G. And so G reacts with 30% aqueous HNO3 to give a red brown octahedral ionic complex. Again a red brown. So you know this is yellow. And you can HNO3, you add HNO3 and you obtain red brown. Okay, don't forget this is red brown. And the oxidation state of Fe remains unchanged. So this is a crucial point. Because normally when you have this iron 2 plus, here this is in iron 2. When you have HNO3, basically iron will be oxidizing in Fe3 plus. If you remember about your cation analysis in group 2, after we do the precipitation, to precipitate out in group 3 before we remove H2S and then you add nitric. Why you add nitric? To oxidize Fe2 plus to Fe3 plus, right? But here, don't forget, they have mentioned this oxidation number does not change. Okay, so this is a crucial point. The oxidation state of iron remains unchanged during this reaction. Okay, the molecular formula of L is this. They have given this, right? The structural formula. So think about this. It is Fe. Now I have to use this one. Okay. The molecular formula should be Fe, 1 Fe, and there should be 2 potassiums, 5 carbons, 2 nitrogens, and 1 oxygen. Okay, so this should be the one that is according to the evaluation. And what can you expect? Because since you have 2 potassiums, so basically there should be 2 potassium in the front along with the complex. And you need to understand what is actually happening with this nitric. That is important to understand, right? So according to the information, Fe, 2 potassium, 5 carbon, and 2 nitrogens, and oxygen, right? Yeah, so it should be, yes, 6 nitrogen, in fact. Right, so what is actually happening when you have this cyanide that is undergoing a red-brown complex? The important thing that you need to understand here, the oxidation state of iron does not change. So basically there should be K2, which is similar to this one, and there should be iron +2 here. Okay, so this is also +2. So the overall entire charge should be around -2. Okay, so +2, -2. So you need another like -4 in order to make it happen. Okay, so think about this thing. There was cyanide, 6 cyanide ligands. But what is happening here when you add HNO3? That is essential to know. But don't forget, they have given the formula, the composition as well. So if you think about cyanide groups here, just think about these cyanide groups. There is 5 carbons. And if you think there is still cyanide groups that is left, so there should be 5 nitrogens as well, which should give you the idea this is CN5. Okay, so what is remaining here if that is CN5? The only thing that is remain here is NO. Okay, you should understand this. This is important to understand. Okay, so if you understood this one, you can automatically write down the formula because you know this now, what is actually happening here, right? So cyanide 6 ligands were initially there, but when you add HNO3, you can imagine one of the cyanide, see 6 cyanides to 5 cyanides. So one of the cyanide is now replaced by a NO group, which in this formula now there can be CN5NO. Okay, so now we can check this should be -5 and this should be +1 because nitrosyl NO is +1. So basically -5 and +3, the overall is -2, which is -2 of the complex. To balance this -2, we have K2. So this is the formula that is given, and this is the structural formula. K2 and the complex is FeCN5NO, or either FeNOCN5. You can write down anyway. Okay. So what is happening actually here? The process that happens here is HNO3, NO from HNO3 comes and replace one of the cyanide groups here. Okay. So don't forget to count that part. Okay. So try to understand that part. So I will again share the screen for you. Right. So this is this part. And the reaction taking place in part 5, okay, can be described as a ligand substitution reaction in an octahedral complex. Yeah, that is a ligand because this is there are CN5 initially, which is octahedral, and one of the CN is replaced by NO to form another octahedral basically. Yeah, so from the list given below, identify the entering group and the leaving group with their charges in this substitution reaction. So basically you can, what is happened here? Cn minus leave. So Cn minus, there should be Cn minus, yeah. So -1 charge, Cn minus is leaving. And NO is coming from HNO3. So basically NO plus, that is why this charge became 2 minus, right? So the entering group is NO plus with the positive charge, and the leaving group is Cn minus with the negatively charge. Okay. So this is essential to understand. Right, so we are very end. We are to the very end of this discussion. So we can go through this. Wastewater generated. So this entire part belongs to a little bit of inorganic chemistry and calculations. And here part B is generally with electrochemistry. So see where this electrochemistry is. Wastewater generated in an industrial process, pH 7, contains a colored compound D, okay. And they have planned to remove this colored compound using electrochemical oxidation. So they have given what is the reaction that they are going to perform. So basically D is oxidized to A2 plus B and 2 electron is removed. Meanwhile, there should be a reduction which is commonly happening when there is an oxidation. There should be a reduction as well. So water gets reduced into a hydrogen and OH minus. Okay. And they have found the concentration of compound D in wastewater was found to be 0.001. So it is very surprising thing, because it is not easy like to find 0.01 thing, because you don't know what is D. If you know D, then it's okay. Like for an example, if you know this is mercury in the wastewater, then you can find sort of some methods, like you can use atomic absorption spectroscopy, many other methods to find it. But when you don't know what is the impure thing, then it is very difficult. Somehow, so they have found D, the concentration, and calculate the time required for this complete electrochemical oxidation of compound in a 1 decimeter sample of wastewater by electrolytic cell consists of 2 platinum electrode using a constant current 100 milliamperes. So basically what they have done, so we will use the board very quickly. Okay, so this is our electrochemical cell. So we have, no, I will just draw a little bit towards, because I can do the calculation on the right hand side. So this is our electrolytic cell. So this is connected to the battery. So negatively charged should be this, positively charged should be this. So this is the place where our cathode lies, and the reduction is going to happen. And this is the place where our oxidation is going to happen. Okay, and the current that is going is 100 milliampere, which is given, and we have used 1 decimeter of the sample. That is nice. So you know the 1 decimeter. So you know the concentration of D here is 0.001 m. Okay. And the oxidation process, you know, here the oxidation process is given, that is D. I will not going to put here the physical states, but you need to know those things. So A2 plus BAQ and 2 electrons, and the reduction is 2 H2O liquid plus 2 electrons, giving H2 gas and 2 OH minus. So this is the oxidation reaction that is going to happen in this electrode, platinum electrode, and this is the reduction that is going to happen in this platinum electrode. So these two are inert platinum electrodes. Okay. The first question asks, calculate the time required to complete oxidation. Okay, so the 1 decimeter sample, and you need to completely oxidize. So think about this, right? The concentration of D that is given here is 0.001 m. So you can imagine the number of moles of D present in this solution is also 0.001. Why? Because they have used 1 decimeter solution. So you can write down number of, I will show the board, see the board now. Yeah. So number of moles of D is 0.001 mole. Okay. Then according to the stoichiometry of this oxidation, you see 1 mole of D produces 2 moles of electron, which means therefore number of moles of electron emitted or given now should be 2 times of this. So basically it is 0.002 moles. Okay. So if you know the number of moles of electron, you can count the charge. How do you get the charge? They have given the information of the Faraday's constant. Okay. So in this question, they have given the Faraday's constant as 96,500. So basically, this is number of moles, and here 96,500 coulomb per mole. So mole to mole get cut. So you know the amount of charges needed for complete oxidation. So it will be 96,500 times 0.002. So you know the charge in coulombs. You know that is in coulombs. So if you know that is in coulomb, you can use Q is equal to IT. So this is A level physics. So even you know this in electrochemistry, Q means the number of charge, which is 0.02 into 96,500. I is given 100 milliamperes. So you can put that in amperes. So 100 into 10 to the power minus 3 amperes, and then multiply it by time. So the only thing that you don't know here is time. So you can calculate time. So this is a simple setup for the oxidation of compound D, which is identified as an impurity, right? So what we did, so we know the concentration of D here. This is 0.01 m, 0.001 m. So you can calculate the number of moles of D, 0.001. Then based on this, you can calculate the amount of electrons that you necessarily need to oxidize D, that is 2 times. So this is 0.002. And if you know this as 0.002, then you can calculate the amount of charge based on the electron moles, and then you can calculate the time. That's it. Okay. So this is question number 1. So you can calculate the time. If a hydroxide, so there is A2 plus here that is formed, and there is a hydroxide that is formed, is completely ionized in the aqueous medium, calculate the pH of the wastewater sample after the electrochemical oxidation. So when the oxidation is completed, you can understand A2 plus will be there in the solution, as well as there will be 2 OH minus that can be present in the solution. So you can imagine here, you know the number of moles of electron that is formed. It was 0.002. Why? D is 0.001. According to the stoichiometry, 0.002 moles of electron released. And this amount of electron should be same here in this particular equation. Okay. So if that is same, the stoichiometry of this electron moles to this OH minus is 2:2. So same number of OH minus should be also present. So basically the amount of OH minus is 0.002, which means you know the concentration of OH minus. Since we have used 1 decimeter, this is 0.002 MOL dm minus 3, right? So if you know OH minus concentration, you can calculate POH, and then you can subtract by 14 to get pH. Okay. So basically there will be 2 into 10 to the power minus 3 OH minus concentration. Then you can use either Kw to calculate first H plus concentration, and then you can find pH. Or otherwise you find POH, subtract by 14 to get the pH. Okay. So this is straightforward. And if the above industry releases wastewater containing compound D at a rate of 10 decimeter cube per second. So basically this is, they have used only 1 decimeter here. And they tell if this industry, I will stop sharing again very quickly. They are telling this oxidation is happening, and meanwhile they are releasing like 10 decimeters per second. Okay, they are releasing 10 decimeter because when this oxidation happens, the water gets cleaned, and they are still removing 10 decimeter cubes per second very fast. So think about that. Okay. At a rate of 10 decimeter cubes per second, calculate the minimum current that must be applied to electrolyte in order to come. So the thing is that they are asking is, now at a current of 100 milliampere for this complete oxidation of D, it needed some amount of time here that we necessarily need to calculate in part 1. In the last question that they asked, if this time is required here, if there is 1 decimeter of the solution, it remains. So there's no problem in oxidation, water gets pure. But they also now try to remove this water at a 10 cubic centimeter per second. So within that 1 second period, remember, for this entire 10 cubic centimeter, this oxidation should be completed very fast. Okay. So they are asking, what is the maximum current or the minimum current that we can supply here in order to do this oxidation very quick? Because when you are removing this 10 cubic centimeter within 1 second, this oxidation should be completed by that time. Okay. And they are asking what is the current that is necessarily needed. So it is also very straightforward, because you know in 1 decimeter cube, you know how much moles of D was present. It is 0.001. So you can calculate that for 10 decimeter cube. So it will be 0.001 times 10. So basically 0.01 moles. Okay. It will be 0.01 moles of D. Then if you know it is 0.01 moles of D, you can know what is the number of electrons that is needed. Basically that is 0.02 moles of electrons. And then again by using 96,500 Faraday's constant, you can calculate the amount of charge that is needed within 1 second. Okay. So if you know the charge, then you know the time which is going to be the 1 second time here, then you can calculate the ampere current value. Okay. So this is again a straightforward calculation that can be taken, right? So that summarizes our discussion. So basically you can go through it, and if you have any questions you can ask in the following class. So again, I will tell the final part. So this was 1 decimeter, you know the number of moles of D. So they are removing 10 cubic centimeter, 10 decimeter cube per second. So you need to calculate within 1 second what is the current need. So you can multiply this by 10 to get the number of moles of D. So that is 0.01. So number of electrons should be 0.02 multiplied by the Faraday's constant to get the amount of charge within 1 second. So charge within 1 second means the current, right? Then you can use this equation. Basically time will be 1 second because coulomb per second is the current, right? Which is the I value. So that is straightforward. Right. So